Okay, so I would like to welcome everyone to the third and final day of the PAS conference. I hope you're all enjoying the program so far. And today as well, we have an exciting session that will be starting with the awardees for the PRACE awards. And for this, I would like to welcome on stage Matej Praprotnik, who's the head of the Laboratory for Molecular Modeling at the National Institute of Chemistry and professor of physics at the Faculty of Mathematics and Physics at the University of Ljubljana. So, Matej, the floor is yours.
Thank you, Eleni, for this nice introduction. As a member of both prize committees for the two prize awards that will be awarded at this conference, I'm delighted to chair these first two morning sessions. And I'm also very excited and happy that I can introduce the first speaker, the first awardee for the PRACE Excellence, HPC Excellence Award, Petros Koumoutsakos. I don't think that he needs a special introduction to this audience, but nevertheless, Petros is a professor at Harvard. He used to be professor at ETH Zurich. He is a member of numerous prestigious societies. He's also an international elected member of US National Academy of Engineering. He is a recipient of ACM Gordon Bell Prize in 2013. He's also, because this is as you can see, so an award that it's actually the stress is on the scientific discovery. He's also a recipient of the ERC Advanced Grant, and I think I can stop here because there's not much time to tell everything what he is. He's a titan, let's say. And please, Petros, I'm excited to listen to your talk. Congratulations. Yeah. Yeah.
Thank you, Matej, and thank you to PRACE for giving me this honor. I very much appreciate it. I would like to tell you about AI, computing and thinking, which is the topic of research that I have been pursuing for about 30 years. And I would like to discuss algorithmic alloys for advancing scientific discovery. For this particular talk, I'd like to appreciate and acknowledge these people who have done the work that I will be presenting. In blue, people that they were members in my lab, and in black, these are collaborators, including Matej, that we have worked together on different projects. But I would like also to say that in our lab, we don't separate disciplines. So these are all the PhD students that I had the honor to supervise and where they are today. And these are some of the postdocs, and I would like also to express my gratitude to ETH Zurich, where I was a professor for 25 years, for giving me the environment and the resources to have interactions with these people. The work also would not have been possible, first of all, without the amazing people at CSS. There is not enough that I can say about their help in my work and in science. I'd like to acknowledge Maria Grazia, everybody, Jean Favre, everybody has been amazing. PRACE has been instrumental in giving us allocations in European supercomputing centers like Jülich. More recently, we have a big project in Lumi that I'll talk about. And also, I have been recipient of time at Oak Ridge National Laboratory. So what is it that we are trying to do? Like many other people, we are interested in modeling complex systems that they have multiple scales, and we are interested in systems that they go from the climate down to the protein. And the question is, can we design methods that can reproduce the system dynamics? And given that these are systems that are operating in different scales, we are interested in developing methods that operate in different scales. We're not the first to have this idea. There's been tons of people who have been thinking about surrogate models, large eddy simulations, coarse-grained molecular dynamics. For example, the usual process that we go about these things is we develop new methods to capture bubbly flows. This is a state-of-the-art simulation that can capture tens of thousands of bubbles using a novel numerical method. You can apply this to waves. You can also apply this to microfluidic devices. So this is the forward simulations. Here's the equations, solve the equations, study the physics. And another concept that has been emerging more recently is the concept of digital twins. So how do these forward simulations may be used in digital twins? So here's a project that we have been collaborating. We have been interested in membraneless electrolyzers. You remove the membrane, so you have a difficulty separating the hydrogen and the oxygen, but you let the fluid dynamics do the job. So having good codes and being able to do simulations that involves lots of bubbles and electrochemistry, you can study electrodes like the ones that they were given to us from our experimentalist friends. This was the device that they were doing at first. Now you run simulations, you do optimization, and then we gave them a new design that we have a patent. It's called the volcano design. It's shown to separate oxygen and hydrogen very well, and then from the optimization, we went back to the device. This is in collaboration with a group of Dimitri Psaltis at EPFL. Again, there is a cycle there, and then this digital twins is a concept that we have been pursuing along with many others. Now, there is an issue with these simulations, and when you do this stochastic optimization we do, these are sometimes expensive simulations. They take a lot of time, so there is a need for having faster simulations, but also there is a need of having new modes of discovery. So everybody is talking about AI today. Can AI help scientific computing? Can AI help in reducing the cost of simulations? Can AI help in discovery? And the other question, if it can, how do we go about that? So this is a question that I asked myself about 25 or 27 years ago when I was a postdoctoral fellow at the Center for Turbulent Research at Stanford University, where I used neural networks in order to represent turbulent flows, to create a reduced order representation of turbulent flows. So actually, at that time, we were interested to reconstruct the flow above the wall by using wall-only information. And I think by accident, we are probably the first to ever do deep neural networks, because we started with two layers, and it didn't work, so we kept adding layers until we were able to get good results. So we had some deep neural nets. The paper took about 4 or 5 years to be published, but the results are, this is original flow from a DNS. This is what principal component analysis, or POD, is giving you, and this is what neural nets will give you as a reconstruction. So these times were kind of lonely times. So I was trying to do machine learning for flow modeling and optimization. This paper would never get published in any journal, so the center was very kind to put it in its research briefs, which were free and nobody cared. And more recently, I published another paper that has the same title almost, and in this paper receives about 2 citations a day, has almost 1,000 whatever. I would tell you the most pioneering paper is this one. But now there is another plot, there is another curve on this plot, and the curve is how fast computers have gone over the years, how fast they have become. And you can see that back in 1997, if we were to use neural nets in one of the fastest supercomputers at the time, for one training of a typical neural network, it would have taken us a year, and today it takes less than 3 minutes. And that makes you think different. So what I have learned in all these 25 years, perhaps this is the only slide that perhaps you may want to take with you. I have learned a few things about scientific computing and AI. First thing that I learned is that scientific computing is about mathematics and mathematical forms. AI is about architectures and modules that one is putting together. I have learned that AI is about statistics and averages, and scientific computing very often is about exactness and very high accuracy. And I have learned also that scientific computing, we care very much about understanding, but AI, in its original definition, it's about goals. You don't care how you arrive to the goal, you care that you arrive at the goal. And what I think is important and exciting for the future is to try to put these two things together. So putting things together is a sign of civilization, and there always has to be something Greek in my talks. So this is about alloys. People started talking or creating civilization where we're able to mix metals and make things that they will be having better properties than the individual parts. So alloys is you mix things together, and what I want you to think about my talk, the same way that we have alloys in metals of this kind, you can imagine now that the red is models and numerics, the green is machine learning tools, and the blue is machine learning tools. So what I'm talking about is algorithmic alloys. And I will explain why algorithmic alloys are better than their individual parts, or where they can be better than individual parts. So the first part that I'd like to say is multiscale simulations of complex systems by learning the effective dynamics. So how did we arrive to that? I was interested in seeing whether neural nets are able to replace numerical methods for solving partial differential equations. So here's the Koumoutsakos-Shivasinski equation. The chaoticity of the system is controlled by this parameter L tilde. We can write a usual numerical method, and if I have a numerical method, I can observe how my flow is evolving in time, which is the y-axis, and x is the space. So now, can I replace now these numerics with neural networks? So what would be the idea is I will get some data, I will have a model, a neural net, I will train it, I will optimize it, and then I would like to see if I can predict the dynamics on the unseen data. So I'm using as data now the solution that I know what it is because I would like to predict it. And I don't have time to explain, but instead of predicting on the full-scale dynamics, we predict it first in a reduced order dynamics. So what we do is we train the neural network for a short-term history, and then we use recurrent neural nets with long short-term memory, and then we try to see how far in the future can we predict after we have trained in the gray region. So right after the training, we are doing OK. A little bit later, we are doing OK. A little bit later, OK. Then we start to fail, and then eventually we fail. So my conclusion is that neural networks cannot replace numerical methods for the long run. Now, I would like to show you also that when someone shows you results about neural networks, you should ask them about the time that the neural networks are predicting what they predict. You see here I have two systems, and here's the chaoticity of one and the other, and you can see that the higher the chaoticity, the faster the method is failing. Nevertheless, one day one of my students came and says, we are in the news, we have predicted chaos. But I said, did we not just say we don't predict chaos? Well, this magazine says we do. And actually, they did say that we predicted chaos. And in all these papers, you can read that we don't predict chaos, or maybe better say it does not. So this is something of the things that we experience today. Now, are we dead? So this failure motivated thinking about finding a solution. So neural nets alone may not be the best way to solve the PDE, but what if we do something else? So this is inspired by work from another pioneer of machine learning in complex systems. This is Yannis Kevrekidis, who came up with a method called the equation-free framework. The idea of Yannis is that you have a few expensive simulations, you collect some data, then you create some reduced order model, and then instead of advancing the simulation, you advance the reduced order model, and then at some point, you have to find a way to go back out from less information to more information. There were two problems with the equation-free framework. How do you integrate in the latent space? This was done using Runge-Kutta and such schemes, and also how do you go from less to more information was a problem. So what we did is to come up very recently, after seeing this thing in front of my eyes for 20 years, of using autoencoders to go to the latent space and then use the decoder whenever you want to go out into the fine-scale dynamics. So this is a way, it's a modular way to combine high fidelity simulations with low fidelity simulations. So this is how the algorithm works. You warm it up, then you run only in the latent space, which is very cheap, and then you go back out to the micro dynamics whenever this is necessary. And of course, the speed up depends on how much time you spend in doing the expensive things versus doing things in the latent space dynamics. Does it work? Let's look at the Koumoutsakos-Shivasinski. Now, I will show you results in the Koumoutsakos-Shivasinski, where we are using now only by staying in the latent space. I never go back because I just wanted to see what's the highest speed up that I can get. And what you see, this is the latent space, how it evolves. And here I have trained it, and after that I evolve it with recurrent neural networks. And just for visualization purposes, I present what happens in the real space. And now you can see that these two things are not one-to-one. But again, here comes the story about statistics. If you look at the phase space, LED is able to capture the phase space quite well, and it's able to capture the phase space quite well by being faster by 2 orders of magnitude. So after the Kuramoto-Shivasinski, let's move to fluid dynamics. We do Reynolds number of 100. And instead of using a very high resolution simulation, we use only 2 degrees of freedom. And then we are able, again, to predict with 2 degrees of freedom. And not only we capture the vorticity field, but with only 2 degrees of freedom, you can get the drag coefficient within 4% of the flow. Now, usually in a machine learning talk, after this, people declare victory on turbulence and say, now we can do airplanes. The natural question is, after Reynolds number of 100, can you do Reynolds number of 1,000? So I will ask this question to myself, and I will answer that I cannot with this method at the moment. And what happens is that we have a lot of errors. We don't get the drag coefficient, but at the same time, the failure is actually interesting because we realize that the biggest errors that we do in the reconstruction is around the cylinder, and that's where vorticity is produced, and that's where actually we need to create special autoencoders that take into account the physics, and that's actually what we are working on at the moment. We have extended with Julia and Matej and others this work in molecules. We can do flows at higher Reynolds numbers now, but I would like to move on and to show you another alloy. And again, as I said, there is a lot of people talk about neural networks, and neural networks are interested, but I would like to argue neural networks are interesting when they're trying them in high dimensions. Nevertheless, people use neural networks in low dimensions, and then there is this method called physics-informed neural networks. The method actually was discovered in 1998. More recently, it was rebranded as physics-informed neural networks. What's the idea? You are trying to solve a problem. You're using as an input an x and a t, and then what you do is to find out the weights of your network. You're doing a minimization of this story. This is a cool idea. It's an interesting idea. The idea is attributed to Elias Lagaris and his co-workers. But now, you see, instead of solving a forward problem, you're solving a minimization problem, so you're expecting to be slower. But at the same time, here's a cool idea, actually, that came from the Kanyadakis group. The same way that I have the boundaries conditions as penalty term, I can also put data. I can put data in different parts of the domain and try to do inference and reverse engineering. So now, I would like to tell you that you can take the good things from both approaches and come up with a much better method. And what's the idea? Again, this is pins. And now remember, when you're discretizing an equation, you have to respect the properties of the equation. When you're doing a hyperbolic equation, you don't use a grid everywhere in the domain. When you're doing a parabolic equation, again, you have to do a consistent grid. And here's actually another idea. Imagine that you take actually the discretization of the equation, and instead of marching forward, you do the trick of pins. You put it as an optimization problem. And now the difference from the forward is that when the optimization finishes, the same as pins, you have the solution everywhere. The idea is simple, it's consistent in converging, and it has one more feature compared to pins. It's about 5 orders of magnitude, 4 to 5 orders of magnitude faster. And actually, I'm surprised why people do not compare with these methods in solving different problems. I would like also to show you, if you give me some data, the dots there, and you tell me, here's the equation, find out the k of u. In the red, you can see what pins do. In the purple, you can see what a deal does. Odil also, because of its character, can use second-order optimization, so it's by orders of magnitude better than pins, and we can do a lot of other inverse problems. Nevertheless, pins may be interested in high dimensions, but I would like to see the results on that. In closing this first part, I would like to argue that machine learning is a very interesting tool, but it has to be used cautiously, and where I think we should not abandon the capability of doing forward flow simulations. So these are 25,000, 50,000, 100,000. These are beds in money. This is flow past the cylinder at this Reynolds number also, and I will argue that by my lifetime, machine learning will not be able to simulate these flows. So we should, if we care about what does a flow look like at 100,000, this is what it looks like, and I think we will not be able to get it without doing simulations like this and without training people to create code that uses adaptive mesh refinement, etc. I'm showing you this simulation because this is probably the highest ever resolved flow simulation because we are in 2D and we are using a few billion grid points of effective resolution. Now, alloy number 3 is the one that I'm the most excited about, and which I think presents a way of putting together machine learning and scientific computing to try to complement strengths. First of all, what is scientific multi-agent reinforcement learning? For a moment, I want you to see this from the point of psychology, is the behavioral changes due to experiences. You have actions, a stimulus and reward. We know the Pavlov's dog. You know how you train kids or athletes or others. And so the idea is that if you have a stimulus action pattern that is rewarded, the actor is conditioned to this particular behavior. There's a lot of work in psychology, and I'd like to say that the beginning of this type of research started at Harvard, and this was at a group of burro Skinner, who was actually trained pigeons.
The two pigeons are at either end of a small ping pong table. One pigeon pecks the ball as it comes toward him and knocks it toward the other pigeon. The other pigeon pecks the ball back across the table. If it goes past one pigeon, the other pigeon can eat, and if it goes the other way,
so
the pigeon
you see,
it's a real game.
Every time a pigeon scores, there is a door that opens and the pigeon eats. So the pigeon learns that if I score, I get to eat. So it learns to play ping pong. And now, can you imagine what was the application of this project? What? So the application, this happened at the time of the Cold War. So the idea is that you make the pigeons to be pilots in missiles. You train the pigeons with a particular image of a landscape, and whenever the missile flies over this landscape, the pigeon pecks on a button, the missile goes down, and the rest is history, but thank God this history never materialized. So what is reinforcement learning instead of having pigeons? Here's an algorithmic view. What you do is you have an environment, you take an action to the environment, so you influence the environment, you observe a state of the environment, and then you also receive a reward from the environment. Deep neural networks are very interesting because that's how you encode the relationship between the states and the actions, and you're using the weights of the neural net that you're adjusting in order to maximize the long-term rewards. This is a very interesting process, a stochastic process. In a sense, you do a maximization of an expectation over the policy that connects the states and the actions. And what is interesting also is that it's actually a fascinating thing for parallel computing, because at each time, you can have multiple runs running on different processors, and then the idea is that you're collecting and you're comparing the different experiences. So as you have these different experiences when you play the game, the question is, when you're presented with a new problem, which one of these experiences are you going to use in order to solve your problem? It's a very relevant issue to things that we do in our everyday life. And what is important for the parallel computations is that you can imagine for every one of the seeds that you have, for every one of the runs that you have, because you have different parameters, the processors may stop at one time or another. So load balancing is very important for these things. So we have developed a framework called Corally. It's a load balanced oriented, it has task stealing and other good things to do high performance UQ, stochastic optimization, and in particular reinforcement learning, and it's open source and can be downloaded. And I think you would be very rare that you see strong scaling in the number of nodes that goes like that, and simply because the nodes are completely full all the time because of the task stealing capabilities. So the reinforcement learning and this framework are paradise for, I think, high performance computing. Now, there is one more thing. When you use these past experiences, what you do is you have to be careful that when you're doing the sampling using past experiences, they have to be relevant to the current experience. This is an issue that we addressed with a novel algorithm that not many people know, so I advertise it here. It's called Remember and Forget Experience Replay. So it tries to do good, important sampling. That's basically what it does. Instead of sampling from one probability distribution, you sample from another. So you want these two probability distributions to be relevant. So that's what we did for reinforcement learning with Guido. Applications, one application, which was my ARC grant, was to study collective swimming. So we want to study how fish swim together. So now you're going to see one of the biggest simulations in fluid mechanics ever made. So here it is, actually not this one, this is two fish. I hope I have the... And what you see, what I wanted to say is fish interact hydrodynamically. This is one of the biggest simulations ever made. This is about 300 fish. I asked for 300 and they gave me 310. So in any case, what you see is this DNS of 300 self-propelling animals. And what you will see is you start with a configuration, but because of the hydrodynamic interactions, they do not stay together. So we want to control dynamically their behavior so they can stay together. This is running using trillions of elements on Lumi. So what we do is we do reinforcement learning. You have a fish that swims and another fish that is adapting its behavior by observing the swimmer in front, and it tries to adjust its swimming to achieve different rewards. One of the rewards that we wanted to have is swim efficiently. So we have the swimmer down there that can do whatever, and this one up there, this is what it does if it wants to swim efficiently. We actually found that when it starts to swim, actually it realizes eventually that it has a benefit to go and swim right into the wake of the other swimmer. This is fluid mechanics discovery. This is not something I would have discovered by myself, no matter what the fluid mechanics I know. Reinforcement learning did this in an automated fashion. This is early stages of learning. At later stages of learning, it finds a beautiful ballet where it anticipates vortices, it generates dipoles, and that's what reduces the drag. And that's actually what we do also for three-dimensional flows now. This is again a state-of-the-art simulation that includes lessons learned from reinforcement learning, where we actually teach the swimmers now to take and harness the vortex rings that are coming from the three-dimensional swimmers, and we can get different efficiencies in different configurations. There are tons of applications of this. One of them is the arrangement of wind turbines, but I would leave it at that for perhaps another talk. And now I will close with one part that I am super excited about, which is to use reinforcement learning to create closures for PDEs. That you have together a PDE that is reduced order modeling of a PDE and this multi-agent deep reinforcement learning. And what's the idea? The idea is as follows. That when you're doing LES or you're doing a reduced order model, you are having scales that you not resolve. So you have the same equation with resolved case and scales you don't resolve. And people make a lot of money by coming up with different formulas for coarse-grained this, LES this, runs this. And the idea is, can I use reinforcement learning to do that, to find out the policy? This is easily said than done, but now you will realize that there is a problem. The problem is that if you have a 32-cube grid, you will have tens of thousands of grid elements. That's a lot of states. It's very difficult to solve. But now came the observation. I have made few observations. This is one that I made, that usually when you have a grid, you update based on numerics. But now, what if you see the grid points not only to be numerical quadrature points, but also to be agents that learn? So now you give work to the grid points that they are both learning agents and things that they're observing the equations. So this is MAD reinforcement learning, multi-agent deep reinforcement learning. The idea is the grid points have a dual role and has lots of interesting things compared to other things, has limited data. And I'll show you a couple of results because Matej is anxious. So the results is homogeneous turbulence is one, where we are trying to compare with direct numerical simulation and state-of-the-art models. And we find that we train for a few Reynolds numbers, but we are able to extrapolate to higher Reynolds numbers. Even when you train to only one Reynolds number, you are able to extrapolate and you outperform the state-of-the-art. And there is one more thing that we did. We did also wall-bounded turbulence. People say you're never going to be able to solve the flow around an airplane. You have to model the near wall region. We did this with Jane Bai from Caltech. Again, the key thing is what it is that you observe, how do you act, and how it is your reward. And to me, this is one of the best results that I have seen in machine learning, in the sense that we train up to RE tau of 10 to the 4th, and if we choose a good policy, because we can have also a bad policy, we're able to extrapolate RE 10 to the 6th. And not only we can take the channel flow and advance in Reynolds number, we can take also this the same policy and apply it to a turbulent boundary layer, and we really nail the experimental results for this flow. I think I would like to close with an observation. This is from Judea Pearl, the Book of Why. And I would like to say that Judea, one of the pioneers of machine learning, argues that machine learning is nothing but association. Where we go, if we want to go up the ladder of causation, is you start to do intervention. I like reinforcement learning because you intervene with the things you study. And I think there will not be a day that machine learning or other things will replace imagination. However, they will complement imagination and retrospection and understanding, and we live in exciting times, and I want to thank you.
Thank you very much, Petros, for this very exciting talk. I'm sure there are questions in the audience. Yeah, Philip. Let's go.
So thank you for this brilliant talk. That makes me happy to work for PRACE and to have contribute to that. Honestly, very beautiful one. I have a question. What about quantum computing? Do you think that could be helpful in some of your machine learning algorithm?
I know nothing about quantum computing, even though I have spent a couple of years trying to learn about it. If you are able to do stochastic optimization in a quantum computer, that would be very interesting for this type of applications. But I don't know how to do it, so I cannot. I'm reading into it. I have not understood yet to be able to tell you.
Okay, so rendezvous in a couple of years.
Yeah, with pleasure. Yeah, with pleasure. It's a very fascinating topic indeed, and I share the curiosity that you have. Yeah.
Thank you. Any other questions? Are there any questions from the online?
No, not online. But maybe I can ask you, since you mentioned physics, which I think is the underlying principle of why neural networks are not just enough. I was wondering, what do you think is the best way to incorporate physics? Is it through constraints? Is it through architecture of our equations, or even the network architectures? What would be the best way to account for it?
I think if you incorporate invariants, if you incorporate symmetries, and if you incorporate interest in physics, then you are helping the neural net. At the same time, if you try to replace a hyperbolic solver with grid points everywhere, you're doing damage. So I think if you do reduced order models, neural networks are beautiful for that. And if you go to high dimensions, neural networks are beautiful of that. And how you train them is also very interesting. For our reinforcement learning, if we did not use as states for this, the invariants of the stress of the gradient tensor and the Laplacian tensor, for 2-3 years, a lot of people were working on it and nothing worked. The idea was there, but if you don't incorporate physics in what is your states, and if you don't incorporate domain knowledge, it doesn't work. The same for LED. If you don't incorporate domain knowledge as to which data you should train your autoencoders on, again, I want to iterate that I believe in the combination of the two.